Hello, everyone. Welcome to the Analog Electronic Technology course. Previously, we introduced the methods for determining AC and DC feedback and positive and negative feedback. In this lesson, we will continue by discussing other types of feedback, namely, series and shunt feedback, as well as voltage and current feedback. Generally, series and shunt feedback in voltage and current feedback are considered in the context of AC negative feedback. Let's start with how to determine series and shunt feedback. Series and shunt feedback refer to how the feedback network is connected to the amplifier's input. When the feedback network feeds a signal back to the input, it can be connected at the input in either a series or shunt manner. Series and shunt feedback are determined by how the feedback network is connected to the amplifier's input. In series feedback, the input of the basic amplifier and the output of the feedback network are connected in series. In this case, the signal in the input loop sums as a voltage, satisfying Kirchhoff's voltage law, KVO. Minus VI plus VID plus VF equals 0, which means VID equals VI minus VF. Therefore, to achieve a noticeable feedback effect, changes in VF should effectively cause changes in VID. This is best achieved when VI is a constant voltage source, meaning the signal source's internal resistance Rs should be as low as possible. In other words, for a voltage signal source, series feedback works better. In shunt feedback, the input of the basic amplifier and the output of the feedback network are connected in parallel. At the input, signals add in terms of current, satisfying Kirchhoff's current law, KCO. II minus IID minus IF equals 0, which means IID equals II minus IF. Therefore, to achieve a noticeable feedback effect, changes in IF should effectively cause changes in IID. This works best when II is a constant current source, meaning the signal source's internal resistance Rs should be as large as possible. In other words, for a current signal source, shunt feedback is more effective. So, how do we determine whether the feedback is series or shunt? The key is how the signals connect at the input. When the feedback signal XF and the input signal XI are connected to the same input, it is shunt feedback. For example, the following three common connection types in transistor and op-amp circuits all fall under shunt feedback. When the feedback signal XF and the input signal XI are connected to different inputs, it is series feedback. For example, the following circuit wiring configurations all represent series feedback. Now, let's use specific examples to determine whether a circuit employs shunt feedback or series feedback. First, look at this circuit, where we are asked to analyze whether the interstage AC feedback is series or shunt. It's obvious that the input signal is applied to the non-inverting input of the first stage op-amp A1, and the interstage feedback signal is fed back through resistor R2 to the same non-inverting input of A1. Since the input signal and feedback signal connect to the same terminal, the interstage feedback here is shunt feedback. Next, consider this circuit, where we also analyze whether the interstage feedback is series or shunt feedback. Here, the input signal is applied to the input T1 of the differential amplifier, while the feedback signal is fed back to a different input T2. Since the input and feedback signals connect to different terminals, this is series feedback. Previously, we learned that series and shunt feedback are determined by how the feedback network is connected to the amplifier's input. Next, let's look at two other types of feedback, voltage feedback and current feedback. Voltage and current feedback are determined by the sampling point of the feedback network at the amplifier's output. If the input of the feedback network is connected in parallel with the amplifier's output, as shown in the diagram, this implements voltage sampling. This is similar to how a voltmeter measures voltage. By connecting in parallel with the component, it can measure the voltage across it. This sampling method at the output is called voltage feedback. In this case, the feedback signal XF is proportional to the output voltage, that is, XF equals FVO. So, what are the characteristics of voltage feedback? Let's find them out together. When the load resistor RL decreases, the output voltage VO drops accordingly. As a result, the feedback signal XF also decreases. With the input signal Xi held constant, this negative feedback causes the net input signal XID to increase, which in turn limits the decrease of the output voltage VO. This shows that the circuit can automatically adjust the output voltage VO to compensate for changes in the load resistor RL. Therefore, voltage negative feedback plays a role in stabilizing the output voltage. Earlier, we analyzed voltage feedback. Now let's look at current feedback. When the input of the feedback network is connected in series with the amplifier's output, as shown in the diagram, this implements current sampling. This is similar to how an ammeter measures current. By connecting in series with the component, it can measure the current flowing through it. This sampling method at the output is called current feedback. In this case, the feedback signal XF is proportional to the output current, that is, XF equals FIO. Similar to voltage negative feedback amplifiers, current feedback also serves to stabilize the output current. Here's how the regulation works. When the load resistor RL increases, the output current IO decreases. After feedback, the feedback signal XF also decreases. With the input signal Xi held constant, the negative feedback causes the net input signal XID to increase, which limits the decrease in output current IO. Thus, current negative feedback reduces the impact of changes in load resistor RL on the output current IO. In other words, current negative feedback functions to stabilize the output current. We just introduced the characteristics of voltage and current negative feedback. Now, let's discuss how to distinguish between voltage and current feedback. A common method is the load short circuit test. The procedure is to short circuit the load. If the circuit is unloaded, then short the output to ground. At this point, the output voltage is 0. If the feedback signal also drops to 0, it is voltage feedback. If the feedback signal is not 0, it is current feedback. Let's look at a specific example. In this circuit, the feedback path is through resistor RF, and the feedback signal and input signal are connected to the same input of the op-amp, so this is shunt feedback. Is it voltage or current feedback? We use the load short circuit test to find it out. After short-circuiting the load resistor RL, the circuit becomes as shown, operating in an open loop state with no feedback, and the feedback signal is 0. Therefore, this is voltage feedback. Let's look at another circuit. It's clear that the feedback resistor RF returns the feedback signal to a different input than the one receiving the input signal, so this is series feedback. Is it voltage or current feedback? We'll again use the load short circuit test to determine this. Short circuit the load resistor RL. Although the output voltage VO is now 0, the feedback signal Vf is still equal to IO multiplied by Rf, which is not zero. Therefore, this is current feedback. Let's examine one more circuit, the common drain amplifier, which we studied earlier. Resistors Rs and Rl are connected in parallel, forming the AC feedback path. The feedback signal is fed back to the source terminal, while the input signal is applied to the gate, so this circuit uses series feedback. The feedback signal is the voltage Vf. After short-circuiting the load resistor RL, Vf becomes zero, meaning the feedback signal vanishes. Therefore, this is voltage feedback. In this lesson, we've gained a solid understanding of how to determine series and shunt feedback in voltage and current feedback, as well as their effects on circuits. Let's now summarize what we've learned. First, we introduced series and shunt feedback. These two types are mainly judged from the input of the circuit. The method is based on how the signal is connected at the input. If the input signal and the feedback signal are applied to the same input, it's shunt feedback. If they are applied to different inputs, it's series feedback. In a series feedback configuration, signals of the input combine in the form of voltage. In a shunt feedback configuration, they combine in the form of current. Then we introduced voltage and current feedback, which are judged from the output of the circuit. The load short circuit test is used for this purpose. Short the load. If the feedback signal becomes zero, it's voltage feedback. If the feedback signal still exists, it's current feedback. Voltage negative feedback helps stabilize the output voltage, while current negative feedback helps stabilize the output current. That concludes our lesson on series and shunt feedback in voltage and current feedback. Thanks for watching.